In this video, I'd like to talk about the math question of the day for Sunday, April 9th, 2023. And with this problem, we have the integral of this function here, which we can notice is actually a product of two distinct functions. We have the linear function 4x multiplied by the trigonometric function, the cosine of 2 minus 3x. And to answer a question like this, you will need the tools of Calculus 2. So at this point, go ahead and pause the video, see if you can work through this problem on your own. And when you're ready, unpause the video and we can go through this together. Now, assuming that you have attempted the problem, we can work through this together. And if you do have suggestions for future questions of the day, feel free to leave those as comments. Now, I mentioned that it's useful to recognize that we have a product of two different functions here. And with integrals, many of them are incredibly difficult to do. But when you have a product, one method that you can use sometimes is integration by parts. And there is a formula for that, but that formula is often difficult to remember. So one piece of advice is that you can rederive that formula if you know the product rule for differentiation. And let's just rewrite that. If we have two functions, let's say we have p and g, where p is just a function of x and g is also a function of x. Let me rewrite that. If we have this product of functions and we take its derivative, this is equal to the derivative of the first function multiplied by the second function plus the first function multiplied by the derivative of the second function. And with this product formula, this rule for differentiating the product of two functions, we can derive the formula for integration by parts. And we can do that by essentially just taking an integral of each of these terms. So let me write this out a little bit carefully. We're taking the integral of this product, which again is p of x multiplied by g of x, and that's the derivative of this product. And since our independent variable is x, we're taking this integral with respect to x, and we will do the same here. We're taking the integral of the derivative of p of x multiplied by g of x, and that that integral is with respect to x. And then we're adding the integral of the function p of x multiplied by the derivative of the function g of x, and this integral is with respect to x. Now, at this point, we can use the fundamental theorem of calculus that when taking the integral of the derivative, we just get back the function. And in this case, the function is actually a product of two functions. So let's rewrite that. We will just have p of x multiplied by g of x. And I should mention that if this is a definite integral with bounds, we would need to be a little bit more careful, because we would have to evaluate this between the two bounds, but we're dealing with an indefinite integral. We would just have some constant of integration. And over here, we can just essentially rewrite everything because there is no simplifying this. Now at this point, we can just solve for either of these terms and we will have our formula for our integration by parts. So let's solve it for this term here. And we'd say we have the integral of the derivative of p of x multiplied by g of x with respect to x. This is equal to this expression here, p of x times by g of x plus that constant of integration, and we're subtracting this integral here, which is p of x multiplied by the derivative of g of x, and all with respect to x. And like I mentioned, if we do have bounds here, we can put those in. This constant of integration will go away. We'll evaluate this between a and b, and we will also evaluate this integral between a and b. But in this case, since this is an indefinite integral, we don't need the bounds, and therefore we will have this constant of integration. So we have our formula This is the integration by parts formula. And like I mentioned, this can be a little bit difficult to remember. So if you do forget this and you don't have a way to recall this, then you can start with your product rule for derivatives and just rederive it by taking an integral of each of these terms. But with that in mind, we need to figure out how to actually use this formula. And if you want, we can just put this constant of integration at the end. So the key idea with this is to figure out which of these functions we can take the derivative of and create a simpler integral where we don't have a product. And notice that if we took the derivative of x, we would just get back 1, and we can reduce our integral to just an integral with the cosine function, which we do know how to actually compute. So this is the function that we want to take a derivative of in this term right here. So essentially, we can say that in our case, g of x is equal to x or 4x, depending how you want to look at it. We could just factor the 4 out, but let's call this 4x. And the function that we've already taken the derivative of, p prime of x, this is the cosine of 2 minus 3x. And by assigning these two functions the way we did, we will look at this integral here where we take the derivative of g, and that would just be 4. So we'll have a function, or I should say an integral, where we just have the cosine function. So let's apply what we know about this, and let's make a little bit of room here. Now, notice that in our formula, if I go back, the first part has p of x times by g of x. And we have g of x, but we do need to find p of x. So we need to find the antiderivative of this function here. So I'll scroll back over. We need to find p of x. So to do that, we'll take the integral of the cosine of 2 minus 3x dx, and we'll need to perform a u substitution. We can say that u is 2 minus 3x, and du is just negative 3 dx. And we can make a substitution. We know what dx is. If we solve for that here, we'll divide both sides by negative 3. We can plug that in, and we can rewrite this integral as the integral of the cosine of u multiplied by dx, but that is really just du over negative 3, which I will put on the outside as minus 1/3. And the integral of the cosine function, the cosine of u, would just be the sine of u. So we have minus 1/3 multiplied by the sine of u, but u is this expression, 2 minus 3x. And if we're careful, we would have a constant of integration, but we will just add in that constant of integration at the end. So we figured out both p of x and g of x in our formula. So let's rewrite everything. I will copy this first and rewrite it down below. So let's scroll down here, and we can better apply this formula. We have that this integral is equal to g of x multiplied by p of x. We figured out that this right here is p of x, and we know g of x is just 4x. So we have 4x multiplied by p of x, which is negative 1/3, multiplied by the sine of 2 minus 3x. And we can add our constant of integration, or we can wait till the end. So let's do all of that right now. And we will now subtract this second integral, which will be easier to evaluate. We have the integral of p of x, which we know is this expression here, this minus 1/3 multiplied by the sine of 2 minus 3x, and we're multiplying this by the derivative of our function g, and we know our function g is just 4x, so g prime of x would just be 4. So all of this is then multiplied by 4, and we take this integral with respect to x. So our integral has simplified to this expression here, And we just need to evaluate this integral and simplify this a little bit. We can just put the 4x in this numerator here. So let's focus on this integral first. We can factor out the negative, we can factor out the 1/3 and the 4, so that, let me highlight all of this. We have a positive integral. We have 4/3 out in front, we can factor that out, and we have the integral of the sine of 2 minus 3x dx, though since this is a sine function, we can actually evaluate this integral, but before we do that, we will need to do a u substitution. So let's say in this case, u, or maybe we call it u1 since we've already used u, u1 is equal to 2 minus 3x. We take the derivative of that on both sides. We would get -3 dx on the right-hand side, and we can solve for dx so that we can substitute it. Dx would just be du1 over -3. So let's substitute everything in. We have 4/3 multiplied by the integral of the sine of u multiplied by dx, but dx is du1, excuse me, there's a subscript here as well, and then all divided by -3, which we can just factor out. We have -3 multiplied by 3 in this denominator. And this fraction here just simplifies to -4/9, and the integral of the sine of u1 is just the negative of the cosine of u1. So the negative will cancel out, and we get the cosine of u1, but u1 is 2 minus 3x. And we do have a constant of integration, but ultimately all of our integration constants can add together to some new constant. So we can just call that overall constant c. But if you want to be careful, you can call this c1, then we get plus c2, and we can say that c1 plus c2 is equal to c. So if you want, you could do all of that, or just call your overall integration constant c, like we have here, since we really just need one constant in the end. And let's put everything together and simplify. This integral would be this expression, which is minus 4x/3 multiplied by the sine, let me rewrite that, by the sine of 2 minus 3x. We'll put the plus c at the end. And then we have this integral, which we know is plus 4/9, the cosine of 2 minus 3x, and we have plus c at the end. So this should be our final answer, but if we do want to check our work, we can just take the derivative of all this, and if we end up with this original integral, then we know we did this correctly. And if you want, you can also just put this into an integral calculator, and that will check your work very quickly. But I do encourage you to practice taking derivatives once you evaluate an integral, and that way you can do this by hand and you don't have to rely on technology to check your work. But I will leave all of that as an exercise for the viewer.